This conference will now be recorded.
Endocrinology, we have different learning objectives. In this chapter, you will learn the functions of endocrine glands, hormone release and transportation in the endocrine system, and the role of receptors in the influence of the hormones on the cells. Regarding introduction, the endocrine system is a chemical messenger system comprising feedback loops of the hormones which are released by the internal glands of an organism and directly into the circulatory system, regulating distant target organs. In humans, the major endocrine glands, they are the thyroid and the adrenal glands. Survival is not possible if these two hormones are not working. In vertebrates, the hypothalamus is the neural control center for all endocrine systems. The study of the endocrine system and its disorders is called endocrinology. The three major components of the endocrine system are glands, which are specialized cell clusters or organs, hormones, which are chemical substances secreted by glands in response to stimulation, and receptors, protein molecules that bind specifically with other molecules such as hormones to trigger specific physiological changes in a target cell. Glands. The major glands of the endocrine system are pituitary gland, thyroid gland, parathyroid gland, adrenal gland, pancreas, thymus, pineal gland, and gonads. In the females, we have ovaries and testes in the male. So this is general layout of the glands. You can see here that the pineal gland lies here, and then thyroid gland and the parathyroid gland they lie in the neck, and thymus it lies in the anterior mediastinum. Adrenal glands they lie over the top of the kidneys, and the pancreas lies here. This is the retroperitoneal organ, the most posterior part of the abdominal wall, and the ovaries on the testes. And the glands can be classified according to their functions. Hormones, by definition, a hormone is any of class of signaling molecules produced by glands in multicellular organisms that are transported by the circulatory system to target distant organs to regulate physiology and behavior. Hormones are substances released by glands in response to stimulation. They trigger or regulate the activity of an organ or a group of cells. Hormones are usually proteins, glycoproteins, steroids, and catecholamines. Hormones, they have diverse chemical structures and mainly of three classes. They can be eicosanoids, steroids, or amino acid or protein derivatives, like they can be derivatives of amines, peptides, and proteins. The glands that secrete hormones, they comprise the endocrine system. Hormones are used to communicate between organs and tissues for physiological regulation and behavioral activities such as digestion, metabolism, respiration, tissue function, sensory perception, sleep, excretion, lactation, stress, growth and development, movement, reproduction, and mood. Hormones they affect cells, distant cells by binding to specific receptor proteins in the target cells, resulting in a change in cell function. This may lead to cell type specific responses that include rapid changes to the activity of existing proteins or slower changes in the expression of target genes. Amino acid based hormones like amines and the peptide or proteins, they are water soluble and they act on the surface target cells via signal transduction pathway. Steroid hormones, being lipid soluble, they move through the plasma membranes of the target cell to act within their nuclei. Cell signaling. The typical mode of cell signaling in the endocrine system is endocrine signaling, that is, using the circulatory system to reach distant target organs. However, there are other modes like, for example, paracrine, autocrine, and neuroendocrine signaling. Purely neurocrine signaling between neurons, on the other hand, it belongs completely to the nervous system. Depending upon their function, the glands can be divided in, say, cell signaling can, on the basis of signaling, the cells can be divided into autocrine, where autocrine signaling is the form of signaling in which a cell secretes a hormone or chemical messenger, which is called autocrine agent, that binds to autocrine receptors on the same cells and leading to changes in the cells. Paracrines. Some endocrinologists and clinicians, they include the paracrine system as part of the endocrine system, but there is not consensus. Paracrines, they are slower acting, targeting cells in the same tissue or organ. An example of this is somatostatin, which is released by some pancreatic cells and targets other pancreatic cells. Juxtacrine, this type of signaling is a type of intercellular communication that is transmitted via oligosaccharides, lipids, or protein components of the cell membrane and may affect either the emitting cells or immediately adjacent cells. It occurs between adjacent cells and that poses broad patches of closely opposed plasma membranes linked by transmembrane channels known as connexins. The gap between the cells can usually be between only 2 and 4 millimeters. So we can understand with the help of this picture also that there are different forms of chemical signaling. Autocrine, like you can see here, the cell is secreting some hormone and it is targeting itself. So it's an example of autocrine glands. Then regarding signaling across gap junctions, here a cell targets a cell connected by a gap junction. Here you can see that this is the signaling cell and there are junctions. So the hormone produced, it will go to the cell, go to the target cell to produce the desired effect. Paracrine, where a cell targets a nearby cell. This is the signaling cell which is secreting hormones, and then this other target cell is lying close to the signaling cell. So this is an example of paracrine activity. Endocrine glands. Here a cell targets a distant cell through the bloodstream. So you can see here that this is the signaling cell which is producing hormones and releasing into the blood circulation, into the bloodstream. And then these hormones, they reach the target cells where they will produce the desired action. Sometimes the hormones are preformed and they are just immediately released into the system. But some of the hormones, they will be present in the body as pre-pro hormones, and they will be converted to prohormones, and which will later be converted into hormones. And some hormones, for such hormones, usually we will need carrier proteins. Carrier proteins are usually required for steroids, thyroxine, and for insulin-related growth factor. So if carrier protein increases, so it means that pre-hormone concentration will be low. So free hormones, they are biologically active. So it will increase trophic hormones and it will increase the total hormones. Or estradiol, it increases levels of binding protein and total hormone, but free hormone level is fixed. We can classify hormones on the basis of their molecular composition and then from which gland they are released and which hormones are being produced. So polypeptides, which are made of many amino acids which are connected by peptide bonds. Mostly, which glands are going to produce it? Anterior pituitary, posterior pituitary, parathyroid, and pancreas. From anterior pituitary, we have polypeptide hormones like growth hormone, luteinizing hormone, follicular stimulating hormone, and thyroid stimulating hormone. From posterior pituitary, we get polypeptide hormones like antidiuretic hormone and oxytocin. From parathyroid gland, we get parathyroid. And pancreas releases insulin and glucagon, and both of these are polypeptides. The glycopeptides, you can see that they will also come from many organs, like and the active hormones are going to be thyroid stimulating hormone, luteinizing hormone, FSH, HCG, Mullerian inhibitory factor, alpha-fetoprotein, renin, and erythropoietin. Steroids, they are derived from cholesterol, and the three organs in the body, they will produce these steroid hormones like adrenal gland, ovaries, and the testes. Adrenal gland, basically they will produce aldosterone and cortisol. Ovaries, they will produce estrogen and progesterone. And testes will produce testosterone. Hormone derivatives, they are taken out from tyrosine, and such hormones are released from thyroid gland and adrenal medulla. Thyroid gland, it will produce T4 and T3, triiodothyronine and tetraiodothyronine, which are derivatives of tyrosine. Adrenal medulla, it will produce epinephrine, norepinephrine, and small amounts of dopamine, and all of these are also derived from tyrosine. Thyroid stimulating hormone, growth hormone, they have like 191 amino acids, and the prolactin has 199 amino acids, and these are glycoproteins. Regarding transport of hormones, when a hormone reaches its target cell or site, it binds to specific receptors and produces physiologic changes, depending upon its target site and its specific action at that site. A particular hormone, it may have different effects at different target sites. Hormones which are produced by placenta. Placenta cannot produce steroids independently like the ovary. It depends upon the precursors they derived from the fetus and partly from the maternal sources. Precursors from fetal origins, they are required for synthesis of estrogen. Low density lipoproteins, cholesterols, they are derived from the mother, and it is used for progesterone synthesis. Prostaglandins and leukotrienes, these hormones are collectively known as the eicosanoids, and they are derived from the arachidonic acid, and synthesis usually occurs in the cell wall. As you know, that cell wall, it is a bilipid cell layer. It has lipoproteins and it has lipid bilayer, and from the arachidonic acid, rest of the hormones are produced, substances are produced. Sex hormone binding globulin is important in circulation. Some of the hormones, they are bound to the carrier proteins we talked earlier. The free hormones or unbound hormone is biologically active and available to bind to specific receptors. All steroid hormones, they are bound to some extent to the albumin. The majority of the principal sex steroids, they are bound to sex hormone binding globulin, which is a globulin that transports androgens like testosterone, dihydrotestosterone, androstenedione, dehydroepiandrosterone, and estradiol in the plasma. Sex hormone binding globulin is produced in the liver. It binds testosterone with an affinity 50,000 times greater than that of albumin, which is also a carrier protein. However, none of the steroids are metabolically active in the bound form. Serum levels of the sex hormone binding globulin, they are increased by estradiol and decreased by testosterone. If this hormones level, they will rise in certain conditions and they will be reduced in certain conditions. Reduced level of sex hormone binding globulin is seen in cases of hypothyroidism, obesity, Cushing syndrome, nephrotic syndrome, acromegaly, and elevated levels of growth hormone. Then testosterone, corticosteroids, androgens, progestins, insulin-like growth factor. In their presence, we will get reduced levels of sex hormone binding globulin. Increased levels will be seen in cases of cirrhosis of liver, hyperthyroidism, pregnancy, estrogen use, and advancing age. Hormones can be bound to albumin, sex hormone binding globulin, or they can be found in free or unbound form. Estrogen, just 2% of estrogen will lie freely, so this is biologically active. 58% is bound to the albumin, and 40% is bound to the sex hormone binding globulin. Progesterone, just 1% or less than 1% will be biologically active. It will be free. 54% is bound to the albumin, and 48% is bound to the trans-cortin. This is the difference between estrogen and progesterone. So progesterone is not bound to sex hormone binding globulin. It is bound to trans-cortin. Dehydroepiandrosterone, 4% is bound free in the plasma, and 88% is usually bound to the albumin, and 8% is bound to sex hormone binding globulin. Testosterone, just 1% is biologically active because this is free fraction, 30% is bound to the albumin, and 69% is bound to sex hormone binding globulin. Regarding hydrotestosterone, again, biologically active percentage is like 1%, 71% is bound to albumin, and 28% is bound to sex hormone binding globulin. Androstenedione, 7% is bound free, 85% is bound to albumin, and 8% is bound to the sex hormone binding globulin. Important for you to remember the molecular weights of different hormones, like less than 10,000 kilodalton. And then we will go to the specific proteins, we'll talk about them. We will go to the specific hormones, then we'll talk about them, but this is a high yield for you because some of the basics they will ask you. You don't have to remember all of them, just remember the more important substances. Like less than 10,000, 3,500 for calcitonin, 3,500 for glucagon, 4,500 for insulin, adrenocorticotropic hormone, and insulin-like growth factor. Its molecular weight is 7,000. Parathormone, this is a big hormone, so its molecular weight is 9,500. Some other hormones, their molecular weight is more than 20,000, like 1,500 for growth hormone, human placental lactogen, and you should remember that growth hormone, it can be up to 22,000 daltons, 23,000 for erythropoietin, and 24,000 this is for prolactin, and in the more than 30,000 molecular weight, dalton molecular weight, you should remember that 30,000 is for SH and LH, 32,000 for inhibin, and for HCG gonadotropin, this is 38,000. And some molecules, they are even larger, like 65,000, this is the size of renin, and growth hormone, and hydroglobulin, it can be like 660,000. Regarding receptors are proteins which are classified into different types. They can be intracellular, or they can be intranuclear, or they can be on the cell membrane. You should know about certain concepts. What is upregulation? Upregulation means an increase in the number of the receptors on the surface of the target cells. So, and if the number of the receptors is increasing, then it will make the hormone cells more sensitive to hormones. So this is called downregulation. Regarding intracellular or the nuclear receptors, steroid hormones, and then T3, vitamin D, retinoic acid, they all can bind to the intracellular nuclear receptors. So hormones must enter intracellular space. So biologically active as long as the hormone is attached to the receptor only. The moment the hormone is detached from the receptor, the action will be lost. And they are structurally related to some oncogens. So long half-life, so we need very low concentration to work. For example, in cases of endoplasmic reticulum. Short half-life, so if a hormone has short half-life, then we need high concentration to work. For example, prolactin, corticotropic hormones, and corticotropin releasing hormones. So such receptors, they consist of two binding subunits and one DNA binding unit. Hormones attached to DNA binding units, then they will bring about some conformational changes, and which will replace heat shock proteins 90, which are inhibitory proteins, and they will expose DNA binding units, and gene activation will take place. It will lead to expression, and products action will be produced. Second type of membranes, they are the membranous receptors. These are protein hormones, and they just bind to the surface receptors, and they do not enter the cells. So we can get simple receptors, and we can get the G protein linked receptors. So enzyme-linked receptors, they cross the cell membrane just one time. You can see that they are just spanning the cell membrane just once. While the G protein linked receptors, they will go across the cell membrane 7 times. You can see here. So they cross cell membrane 7 times, and ammonia ions, they will go out, and the oxalate ions, they will be on the inside of the cells. Amine ions, they will be on the outer surface, and the oxygen COOH, they will be on the inner surface of the cell. An extracellular part is specific for the hormone, and when the hormone binds to these receptors, they will activate AC and adenylate cyclase, and so the level of the cyclic AMP will increase, and it will increase the level of the protein kinase. So which hormones, they will go to the simple receptors like growth hormone, and they will act through the cytokine I. Prolactin again through the cytokine I receptor, and the growth factors through in insulin-like growth factors, they are like tyrosine kinase. Insulin receptors, they are also tyrosine kinase receptors. Regarding G protein linked receptors, which hormones will act through them? Gonadotropin releasing hormone, then gonadotropins like FSH and LH and HCG. Thyroid stimulating hormone, thyrotropin releasing hormone, oxytocin, antidiuretic hormone, adrenaline, arginine, then serotonin and somatostatin. Hormone release and transport. Although all hormones, they release the results from endocrine gland stimulation, the release pattern of the hormone, it varies greatly. For example, corticotropin, which is secreted by the anterior pituitary, and cortisol, which is secreted by the adrenal cortex, they are released in spurts in response to body rhythm cycles, and levels of these hormones, they peak in the morning. Secretion of parathyroid hormone, parathormone, which is coming from the parathyroid gland, and the prolactin, which is coming from the anterior pituitary gland, it occurs fairly evenly throughout the day. So their levels don't fluctuate. Secretions of insulin by the pancreas, they can occur at a steady rate or sporadically, depending upon the blood glucose levels. Diurnal variation is characteristic of hormones such as cortisol, testosterone, and melatonin, and to a lesser extent, growth hormone. Like growth hormone is also released in pulses. The pulses, their frequency is higher in the initial 1 to 2 hours of the night when someone is sleeping and goes into deep sleep, then the frequency of the growth hormone pulses will be higher, and later it will go to a basal level and then decrease. During sleep, there is a fall in the circulating level of cortisol, insulin, and adrenaline, whereas that of LDH and the growth hormone, it will increase. During sleep, antidiuretic hormone levels increase, and this rises as plasma osmolarity rises. Water is lost but not replaced during sleep. Growth hormone levels will increase, and they will allow growth and metabolic anabolic repair of the tissue wear and tear. Adrenaline is released in response to stress, which is again reduced during sleeping. Secretion of insulin and parathyroid hormones, they are even throughout the day. Insulin secretion occurs at a steady rate or sporadically in response to blood sugar level. Hormone actions. When a hormone reaches its target site, it binds to a specific receptor on the cell membrane or within the cell. Polypeptides and sometimes amines, they bind to the membrane receptors, and the smaller, more lipid-soluble steroids and the thyroid hormones, they diffuse through the cell membrane and they bind to intracellular receptors. What are the effects on target sites? After binding occurs, each hormone produces unique physiologic changes depending on its target site and its specific actions at that site. A particular hormone may have different effects at different target sites. Regarding hormone regulation, to maintain the body's delicate equilibrium, a feedback mechanism regulates hormone production and secretion. The mechanism involves hormones, blood chemicals, metabolites, and the nervous system. And this system, it may be simple or complex. In the body, there are different feedback loops. Negative feedback mechanisms, they help regulate the endocrine system. Simple feedbacks, they occur when the level of one substance regulates the secretion of hormones. This is simple loop. For example, a low serum calcium level stimulates the parathyroid gland to release parathyroid hormone. Parathyroid hormone in turn promotes resorption of calcium from the GI tract, kidney, and bones, and a high serum calcium level will inhibit parathyroid hormone secretion. Here you can see that just one substance like the level of this calcium is controlling the release of one single hormone, which is parathyroid. Then we can have complex feedbacks like hypothalamic stimulation. It can also trigger a complex feedback mechanism. First, the hypothalamus sends releasing and inhibitory factors and hormones to the anterior pituitary. In response, the anterior pituitary secretes trophic hormones such as growth hormone, prolactin, and corticotropin, thyroid stimulating hormone, follicle stimulating hormone, and luteinizing hormone. At the appropriate target gland, these hormones stimulate the target organs to release other hormones that regulate various body functions. When these hormones they reach normal levels in the body tissue, a feedback mechanism inhibits further hypothalamic and pituitary secretions. Like here we can see that different hormones. Here the key is that the green means that there is excitatory response, and then this red orange shows inhibitory response. Hypothalamus will affect anterior pituitary, and then anterior pituitary is going to produce certain hormones, like you can see here, corticotropin, then thyroxine, FSH and LH, and then you can see what will happen. These tissues, these hormones like corticotropin, it will go to the adrenals and it will produce aldosterone and cortisol. And similarly, TSH, it will affect thyroid gland and then it will produce T3 and T4. Once in the body tissue, a good amount of these hormones is produced, it will go back. You can see this trend and it will exert negative feedback. FSH and LH, when they go to the testes, then testosterone is produced. And when these FSH and LH they go to the ovaries, then estrogen and progesterone is produced. And once enough level of FSH and LH is present and there is enough estrogen, then this estrogen is going to have negative feedback on the anterior pituitary. Testosterone, thiazolidine, and thyroxine, cortisol, all of these are going to have negative feedback to the anterior pituitary. If there is plenty of prolactin and growth hormone, then the negative feedback is exerted on the hypothalamus. This picture is important for you to have a good concept of the working of the endocrine system and how the negative feedback and the positive feedback loops work in the body. These things are quite mathematical. Signaling secretory cells. For normal function, each gland must contain enough appropriately programmed secretory cells to release active hormones on demand. Secretory cells they need supervision. A secretory cell cannot sense on its own when to release a hormone or how much to release. It gets this information from sensing and signaling systems that integrate many messages. Together, stimulatory and inhibitory signals, they actively control the rate and duration of hormone release. When released, the hormone travels to target cells where a receptor molecule recognizes it and binds to it. A hormone acts only on cells that have receptors specific to that hormone, and the sensitivity of target cells depends on how many receptors it has for a particular hormone. The more receptor sites, the more sensitive the target cells. So you can see here that this is the capillary, and here is the blood is circulating through it. The blood goes to the hormone. It can contain the hormones which are coming from the glands, and these hormones they will reach the target cells. They will bind to the receptors on the surface, or if they need to go inside the cells, they will go inside the cells. So these hormones are going to have their actions on the target cells, and you can see that there are other non-target cells also. And some of these hormones, they will just exert their actions through the surface receptors or the membrane receptors, and which are the extracellular receptors. And some of these hormonal substances, they will enter the nucleus and they will bind to the intranuclear receptors like the steroid hormones, and then they will bring about transcriptional changes into the nucleus, and then action of the hormones will take place. The mechanisms that control hormone release, basically there are four mechanisms which will control hormone release, like the pituitary target gland axis, then the hypothalamic pituitary target gland axis, then the chemical regulation, and then nervous system regulation. Pituitary target gland axis. The pituitary gland, it regulates other endocrine glands and their hormones through secretion of trophic hormones, which can be releasing and inhibitory hormones. These hormones include corticotropin, which regulates adrenocortical hormones; TSH, which regulates thyroxine and triiodothyronine; luteinizing hormone, which regulates gonadal hormones. In fact, the pituitary gland gets feedback about target glands by continuously monitoring levels of the hormones produced by these glands. If a change occurs, the pituitary gland corrects it in one of the two ways, like by increasing the trophic hormones, which stimulate the target glands to increase production of the target gland hormones, or by decreasing the trophic hormones, thereby decreasing target gland stimulation and target gland hormone levels. Hypothalamic pituitary target gland axis. The hypothalamus also produces trophic hormones that regulate anterior pituitary hormones. By controlling anterior pituitary hormones, which regulate the target gland hormones, the hypothalamus affects target glands as well. Chemical regulation. Endocrine glands not controlled by pituitary gland, they may be controlled by specific substances that trigger gland secretions. For example, blood glucose level is a major regulator of glucagon and insulin release. When blood glucose levels rises, then the pancreas is stimulated to increase insulin secretion and suppress glucagon secretion. A depressed level of blood glucose, on the other hand, triggers increased glucagon secretion and suppresses insulin secretion. Nervous system regulation. The central nervous system helps to regulate hormone secretion in several ways. Hypothalamus. The hypothalamus controls pituitary hormones because hypothalamic nerve cells stimulate the posterior pituitary to excrete antidiuretic hormone and oxytocin. These hormones are controlled directly by the CNS. What is the effect of stimuli? Nervous system stimuli such as hypoxia, which means that there is deficiency of oxygen, nausea, pain, stress, and certain drugs, they also affect antidiuretic hormone levels. Autonomic nervous system, it controls catecholamine secretions by the adrenal medulla. Stress, the nervous system also affects other endocrine hormones. For example, stress, which leads to a sympathetic stimulation, it causes the pituitary to release corticotropin. Endocrine diseases, these are also part of endocrinology. These are common and they include conditions such as diabetes mellitus, thyroid disease, obesity. Then endocrine disease is characterized by misregulated hormone release, like a productive pituitary adenoma, or it may be due to inappropriate response to signaling, like in cases of hypothyroidism. Then they can also result from lack of a gland, for example, in diabetes mellitus, diminished erythropoiesis in chronic kidney failure. And here, the lack of gland in type 1 diabetes, like the cells of the pancreas, they have been affected by certain diseases or conditions, and they cannot produce insulin. Structural enlargement is a critical site. In a critical site such as the thyroid, like toxic multinodular goiter, it will also affect the functioning of the gland. Hypofunction of endocrine glands, it can occur as a result of loss of reserve, hyposecretion, agenesis, atrophy, or active destruction of the gland. Hyperfunction, it can occur as a result of hypersecretion, loss of suppression, hyperplastic or neoplastic change, or hyperstimulation. Endocrinopathies, they are classified as primary, secondary, or tertiary. Primary endocrine disease inhibits the actions of downstream glands. Secondary endocrine disease is indicative of a problem within the pituitary gland. Tertiary endocrine disease is associated with dysfunction of the hypothalamus and its releasing hormone. Hypothalamus, this is a part of the forebrain and it has various nuclei, and you can see that how the thyroid gland and how the hypothalamus and the pituitary gland are linked. It is lying superior and pituitary gland is lying inferiorly. Then hypothalamus has many nuclei which perform different actions and they produce different hormones. Here you can see that this is preoptic nucleus. You don't have to remember all of them, but you should remember the supraoptic nucleus and the paraventricular nucleus because they are producing different hormones. We'll talk, and then the arcuate nucleus because it is also involved in production of several hormones. Paraventricular hormone, paraventricular nucleus, that how they are related to each other, and then how they are related to the pituitary gland. We'll talk about them. This area is called pituitary stalk. If there is injury to the pituitary stalk, it will result in hyperfunctioning of the pituitary gland because the inhibiting action of the hypothalamus will be lost. If you look at hypothalamus, just I have told you that we have paraventricular nucleus, periventricular nucleus, preoptic nucleus, and then lateral to these is lying arcuate nucleus. Then we have supraoptic nucleus and paraventricular nucleus. Regarding blood supply, you can see here that a portal vascular system exists here between the branches of the superior hypophyseal artery and the venous system. This is the median eminence, and here you can see that this is the branches, or this is a inferior hypophyseal artery. The posterior pituitary gland is called neurohypophysis, and the anterior pituitary gland is called adenohypophysis. When it comes to size, the anterior pituitary gland is larger than the posterior gland. So regarding the hormones of the anterior pituitary, we have, you can see that here is this collateral circulation, and through the veins, different hormones are taken to the bloodstream. Prolactin, which is involved with milk production, adenocorticotropic hormone, which is responsible for secretion of glucocorticoids and mineralocorticoids, then TSH, which is responsible for the secretion of T3 and T4, then growth hormone, which will promote growth, and it is important in the lipid and the carbohydrate metabolism. From anterior pituitary, we are also getting gonadotropins like FSH and luteinizing hormone, which are responsible for growth of reproductive system, and sex hormone production, like they will cause secretion of testosterone from the testes in male and secretion of estrogens and progesterone from the ovaries in the females. Regarding the hormones of the neurophysis, we have oxytocin, which will cause uterine contractions, important in the milk ejection reflex, and it also affects the social behavior. Then antidiuretic hormone, it will cause osmohomeostasis, vessel constriction, and also social behavior, like when a person can go and pass the urine and when the person is going to withhold it. So the hypothalamus is connected to the anterior pituitary by portal hypophyseal vessels and connected to the posterior pituitary by hypothalamic hypophyseal tract. So neuroendocrine transducers, they are present in the hypothalamus, in the adrenal medulla and the pineal bone. Regarding anatomy of the hypothalamus, above lies the thalamus, which is separated from it by hypothalamic sulcus. Medially and above the third ventricle, it will form the floor of the hypothalamus will form the floor of the third ventricle into the cerebrum. Then In the lower part of the floor of the hypothalamus, it is connected to the pituitary by pituitary stalk. Anterior to the hypothalamus lies optic chiasma, and posterior to the hypothalamus they lie mammillary bodies. Blood supply of hypothalamus is very important. Gets an independent artery from the circle of Willis, and supraoptic nucleus, it has the richest blood supply, and there are capillaries which are draining into the median amylase. Regarding hypothalamic pituitary hormones, the releasing hormones, thyrotropin releasing hormone, corticotropin releasing hormone, gonadotropin releasing hormone, and growth hormone inhibiting hormones. And other inhibitory hormones are dopamine and somatostatin. Thyrotropin releasing hormone, it has 3 amino acids. It is produced in supraoptic nucleus, and it increases thyroid stimulating hormone production, prolactin, and also adrenocorticotropic hormone in pregnancy. Increases TSH, prolactin, TRH, and thyrotropin releasing hormone, and then it has a role in both primary and secondary hypothyroidism, and it may increase prolactin secretion, and then it can cause galactoria. So high level of TSH, it can cause hypothyroidism, and it can cause hyperprolactinemia. Corticotropin releasing hormone, it has 41 amino acids produced by paraventricular nucleus of the hypothalamus. It increases adrenocorticotropic hormone, melanocyte stimulating hormone, and beta endorphins, and it will be low in chronic exogenous steroid use. Growth hormone releasing hormone, it has 44 amino acids, and it is produced in arcuate nucleus, and it increases the levels of growth hormone. Releases growth hormone analog also, which is tesamorelin, and used to treat HIV-associated lipodystrophy. Gonadotropin releasing hormone, this is a decapeptide. It contains 10 amino acids. Its half-life is just 2 to 4 minutes, and it has autocrine and paracrine effects. It is produced from arcuate nucleus, increases FSH, LH, prolactin by raising estrogen. Released in pulses, high level in follicular phase of the menstrual cycle. It stimulates gonadotropin releasing hormone, stimulates follicle stimulating hormone, LH, and this is suppressed by hyperprolactinemia. Chronic gonadotropin releasing hormone suppresses hypothalamic pituitary gonadal excess. Pulsatile gonadotropin releasing hormone, it leads to puberty and fertility. Amplitude and frequency of gonadotropin releasing hormone, pulses increases in late follicular phase, and amplitude and frequency decreases in luteal phase of the menstrual cycle. Regarding gonadotropin releasing hormones, they can be like low frequency, like 1 to 3 hours, and then they will cause increase in the production of FSH, while the level of FSH is going to stay stable. If the amplitude is higher, then it will cause increased production of luteinizing hormone. If there is high frequency or continuous down regulation, it will lead to decreased production of follicle stimulating hormone and luteinizing hormone. Like you can see that initially they are rising, but when there is down regulation, then you will not see any rise or spike in the level of FSH or LH. An important clinical condition for you, Kallmann syndrome. This is a condition characterized by delayed or absent puberty and an impaired sense of smell or anosmia, and hearing can also be affected. This is more common in males. It is caused by failure of migration of gonadotropin releasing hormones secreting neurons from their site of origin in olfactory bulbs. This disorder is a form of hypogonadotropic hypogonadism, which is a condition resulting from a lack of production of certain hormones that direct sexual development. Defect may be in the placenta or in the ovaries. There will be low production of estradiol pulses, which will lead to no response from the pituitary because of the negative feedback. Melanocyte stimulating hormone, it stimulates production of melanin by melanocyte. It causes hyperpigmentation and Cushing disease. As MSH and adrenocorticotropic hormones, they share the same precursor molecules, which is pro-opiomelanocortin or POMC. So this is inhibitory hormone from hypothalamus. Dopamine, it contains one amino acid and it produced in the arcuate nucleus. It decreases prolactin and growth hormone. It inhibits prolactin, TSH. So dopamine antagonists like antipsychotics, they can cause galactorrhea due to hyperprolactinemia. Another hormone is somatostatin. It has 14 amino acids and it is produced in periventricular nucleus. It inhibits growth hormone and thyroid stimulating hormone. Regarding paracrine effects of somatostatin, it is produced by many tissues, like from the T and delta cells of the pancreas, which will produce this somatostatin, and it will inhibit insulin and glucagon. In stomach, it decreases hydrochloric acid and pepsin production. In intestine, it decreases motility, BIP, intestinal peptides, and motilin, and also CCK-PZ. The pituitary stalk is cut, hyperprolactinemia occurs. Regarding releasing hormones, which are also coming from the hypothalamus, exogenous pulsatile releasing hormone, they increase trophic hormones to reach maximum level. Now, these higher levels are achieved within 20 minutes. Their continuous administration, it will cause down regulation. For instance, gonadotropin releasing hormones, they can be used for contraception. Pulses and release depend on the mainly on the frequency, and they are not dependent on the amplitude. There are certain neurotransmitters which are important in the function of the hypothalamus. These include dopamine, noradrenaline, serotonin, substance P, calcitonin, gamma-aminobutyric acid. All of these are important neurotransmitters. Endorphins, they increase prolactin and they decrease dopamine, increase growth hormone, and decrease frequency of gonadotropin releasing hormone. Regarding functions of hypothalamus, it is involved in regulation of pituitary hormone release. It maintains body weight and calories intake. It is also important for thermoregulation and satiety centers, which controls appetite and thirst. So all of these are maintenance of the weight is also a function of the hypothalamus. To cover endocrinology, we should know all about 5 endocrine glands in the body. These important glands are pituitary, thyroid, pancreas, adrenals, and gonads. Regarding the pituitary gland, you should know that the pituitary gland, it is also called the hypophysis or master gland in the body. It lies in the sella turcica, which is a depression in the sphenoid bone at the base of the brain. This pea-sized gland, it connects to the hypothalamus via the infundibulum, from which it receives chemical and nervous stimulation. I just described the anterior lobe and the posterior lobe for you. Just briefly, from the anterior pituitary, we are going to get TSH, adrenocorticotropic hormone, growth hormone, FSH, and prolactin and luteinizing hormone. From the posterior pituitary, oxytocin and vasopressin is produced. The pituitary gland, it is formed within the rostral neural plate. The Redke pouch, which is a cavity of ectodermal cells of the oropharynx, it forms between the 4th and 5th week of gestation, and upon full development, it gives rise to the anterior pituitary gland. By 7 weeks of gestation, the anterior pituitary vascular system begins to develop. During the first 12 weeks of gestation, the anterior pituitary undergoes cellular differentiation. At 20 weeks of gestation, the hypophyseal portal system has developed, and the Redke pouch, it flows towards the 3rd ventricle and fuses with the diverticulum. This eliminates the lumen and the structure becomes Redke cleft. The posterior pituitary lobe is formed from the diverticulum. The functional development of the anterior pituitary involves regulation of transcription factors, which are expressed in the pituitary stem cells, and dynamic gradient of the local soluble factors. The coordination of the dorsal gradient of pituitary morphogenesis is dependent on neuroectodermal signals from the infundibular bone morphogenetic proteins, which is BMP4. This protein is responsible for the development of the initial invagination of the pouch. Other essential proteins necessary for protein cell proliferation are fibroblast growth factor 8, VNT4, and VNT5. Ventral development patterning and the expression of the transcription factors is influenced by the gradient of the BMP2 and sonic hedgehog protein. These factors are essential for coordinating early patterns of cell proliferation. By 7 weeks of gestation, the anterior pituitary is capable of secreting adenocardiotrophic hormone. Within the 8 weeks of gestation, somatostatin cells they begin to develop with cytoplasmic expression of human growth hormones. Once the fetus reaches 12 weeks of development, the thyrotrophs they begin expression of beta subunit spot thyroid stimulating hormone, while gonadotropes they begin to express beta subunits for LH and FSH. Male fetuses they predominantly produce LH expressing gonadotropes, while the female fetuses they produce an equal expression of LH and FSH expressing gonadotropes. At 24 weeks of gestation, prolactin expressing lactotropes they begin to emerge, and the gland becomes functionally mature.